Hello and welcome back to Crystal Clear. Today we're going to start a new series for formal languages and automata theory. So basically we're going to cover all the formal languages, automata theory and the theory of computation. The things here are going to be really formal. Formally means we are going to define everything mathematically precisely with each and every mathematical details, and then we are going to see what are the repercussions of those things. How do we apply those things in real life? So this entire formal language and automata theory is divided into two broad categories. Firstly, we are going to see the automata theory, and then we'll be moving towards the computability. So obviously, in order to do the computability, in order to understand its concepts, you need to be aware of the automata theory first. So in the automata theory, we're going to have formal models firstly. What do you mean by formal models? How are they defined? We are going to see mathematical definitions of all of them, and also how do we represent them. So DFA, NFA, PDA, regex, grammars, DTMs, NTMs. Through the end of this, you would be aware of what Turing machines are, how do they compute, what do you mean by computation, what do you mean by a computer even, right? Computer kya karta hai? It computes. So using these formal models, we're going to define something called as machines, computers, and then from there, we are going to define languages. Some of the very well-known formal languages. So what are decidable languages, what are Turing recognizable languages, and the very powerful Church-Turing theses. So this is a very great landmark in the entire research of formal languages and automata theory. How do we actually order all these languages which we're going to define together? Then sideways, we're going to see a few important theorems related to these guys, right? Rice's theorem, the recursion theorem, the pumping lemma, and various other things filled in the details, right? After the automata theory is done, we'll be moving towards the computability. Computability basically deals with when you have these languages, the decidable languages of, let's say, even a Turing recognizable languages, how those languages differ when we add in the real computability power. So basically, when we have real time as a factor of an analysis, when we have space as a factor of an analysis, then how do these particular languages differ from each other, right? And how do these formal models that we have already defined, these machines over which we are doing the computations, however they're gonna perform on the basis of either time or space, right? So we're gonna see what time complexity in real great depth. Now this is a bit different from what time complexity you generally learn in your, let's say, coding classes or data structures and algorithm courses, right? So we are going to formally look at what time complexity classes mean, the d time, the n time, all those you must have heard like big O of n square, big O of n cube, all these terminologies. We're going to formally define all these things over here, right? So d time, n time, p, np classes, you must have heard the famous p is equals to np problem. We do not know whether p is equals to np, right? Then exp time and all. We are going to cover the time complexity in great depth. After that, the space complexity is going to come. For example, we're going to see all these complexity classes like the D space, N space, P space, a lot of things to cover. A lot of different reductions, a lot of different languages. You must have heard about various NP complete problems, and like the SAT problem, the 3-SAT problem, the Hamiltonian path, Eulerian path, all these things. How do we actually formalize them? How do we define those as languages, and how do we reduce them to different languages? So we're going to see all of those things. We are going to end up this course with the space hierarchy theorem, which actually is kind of like putting a rubber on these entire languages which we have learned till now, and how do we actually categorize everything whatever we have learned till now into a very nice hierarchical format, right? With this, we're going to start with the automata theory, the very basics of automata theory first. We're going to see each of these formal models one by one, like the DFA, NFA, PDA and all those things. And then we are going to move ahead with the languages. How do we define languages? What are the various different categories of languages? Then the space and the time complexities afterwards. So let us start with the automata theory. In order to understand automata theory, there are 4 important terminologies you must be aware of. So these are the 4 terms which we are going to use throughout the course, right? So let yourself get accustomed to this, right? So we'll be starting with what is known as an alphabet. Alphabet is generally denoted by sigma, the Greek letter sigma. And what is alphabet? Alphabet is nothing but a set of characters. So these are characters A, B, 1. It can be any symbol, right? You can also have a dollar symbol here, any random symbol. A set of those random symbols is called my alphabet. These are like characters. So basically when you are writing words in English language, let's say, so you have an alphabet A, B, C, D all the way up till Z, right? We call those alphabets. In a very similar way, we define our alphabet as sigma. So these are the characters which we'll be using in order to build our language, right? So alphabet is nothing but a set of characters. Then we move ahead with string. String, you can have a correspondence with what we already know as a word, right? So word is made up of alphabets. In a very similar way, what is string? String is made from the characters of your sigma. So sigma में मेरे different characters हैं. What you're gonna do is take characters out of the sigma, concatenate all those characters together, and what you will get is a string. For example, let's say if your alphabet is AB1, you can create strings from this alphabet. Let's say AAB11. This is a string. 2 is not there in the alphabet. So 1 AABBBB. This is again a string. Why? Because 1 belongs to our alphabet, A belongs to our alphabet, B also belongs to our alphabet. And what have we done? We have just taken a few characters from our alphabet and concatenated them. So it forms a string. Now there is a special string which we call as epsilon. Epsilon is called the empty string. So obviously, this is a set, and when we take nothing from this set, we call that string to be an empty string, right? So it has a special symbol known as epsilon. So throughout the course, whenever we say epsilon, it essentially means we're talking about this empty string. The third thing which we need to aware of is a formal language. So हमने सबसे पहले alphabet define किया. We defined a string. Then we are going to define a language. What is the language? Language is nothing but collection of strings over an alphabet. So सबसे पहले हम क्या करेंगे? एक alphabet define करेंगे. After defining an alphabet, we are going to define strings over the alphabet. And a set of any number of strings is called a formal language. I hope this is clear, right? Language, a set of strings. Now let's take an example of some languages. There might be languages which have infinite strings. For example, look at this language. A. What is A? A is a string based on the alphabet. So the alphabet which we have defined is AB1, right? So based on this alphabet, let's say A is a string. Again, A is again a string. A is also a string. A is also a string, and you can go ahead like this, right? So what I have created just right now is a language, because all these are strings which are made from the characters of an alphabet, and a set of those strings is called a language. Now again, there are two special kinds of languages which we have, for whom we have special symbols. So the first is phi. So we denote phi as our empty language. Again, since L, which is a formal language, again a set of strings, so set can be empty, right? So empty set को हम इस phi से denote करते हैं, which represents my empty language. This is different from the language which contains an empty string. So ये दोनों चीजें में आप ध्यान रखना. This language is not equals to the language which contains an empty string, because this is the language which contains no string. So there are no strings in this language. But this is the language which contains one string, which is the empty string. So these are two different languages you need to care about. Right, so we have defined alphabet, string, and formal language. The fourth thing which is important in our automata theory is a machine. Now what is a machine? See, if you look at the formal definition, it's a mathematical function with well-defined rules of getting the output from a given input string. Basically, what do I say? So this is a machine which has some rules for computation. So you have to have defined some rules how you're going to compute. What are you going to compute? So a string W, so let's say W is a string, so W is coming from, so basically W is a set of characters from my alphabet sigma. So given W as an input, this ML machine is going to compute something on it, and at the end of the day, it is going to output. What is it going to output? whether that W belongs to a language, given language, or whether that W does not belongs to a given language. And if it does so, we say that ML accepts the language L. I hope this is clear, right? For example, let's take this language, the language which we have defined just right now. And let's take this as our sigma. So I say that ML accepts this language L if it accepts every string of this form and rejects every other string which is not of this form. For example, so this is my ML machine over here. If you'll give A as an input to the ML machine, it will say, yes, I will accept it. If we'll give A to the ML machine, it will again accept it. But if we'll give B as an input to your ML machine, it is going to reject it. So it is going to accept any string of this form and is going to reject any other string which is not of this form, right? So it accepts every string present in my language L, and if it does so, we say that the machine accepts the language L, or rather we can also have a terminology like the language of the machine is L. So इस machine की language का क्या मतलब है? The language which the machine accepts. Fine. So, and why the machine accepts all these things? So there must be some rules defining the machine, right? How the machine is going to compute whenever an input is given. So we are going to define the rules which will make this machine to accept this particular language, right? So these are the four important terminologies you need to be aware of: alphabet, string, formal languages, and a machine. Now we are going to build upon these four terminologies itself. Just to do a quick recap, alphabet क्या होता है? Alphabet is a set of a few characters. The characters can be any random symbol, whatever you want to keep it in. That is generally denoted by sigma. So sigma represents my alphabet. Strings क्या होती हैं? Strings are concatenated characters from my alphabet. So alphabet में characters हैं. I'm gonna take a few of them. I'll concatenate all those characters together. What I'll get is a string. So obviously you can form various different strings. Formal language क्या होता है? A set of those strings, a collection of those strings which is made over an alphabet is nothing but a formal language. So language is nothing but a set of strings. Machine क्या होती है? Machine is defined actually for a language. So given a language which is a set of strings, machine is defined in a way that it will accept all the strings belonging to that language and it will reject all the strings which do not belong to that language. And how does a machine is able to do that? Machines is defined for a particular rules. So we define mathematical rules for that machine which enables it to accept every string of a given language and reject every other string not belonging to that language. The machine is nothing but a mathematical function, as we are going to see different forms of machines ahead. How are we actually going to create these machines, right? So with this, we are done with the basic terminologies and the basics of our automata theory. In the next video, we are going to start with the different kinds of machines. Those are called formal models like DFA, NFA, regex, DTM, NTM. These are different formal models. These are different types of machines which we have in order to accept different types of languages. So stay tuned. Let's make our concepts crystal clear.